For decades, a single material has reigned supreme in the realm of jet engines: nickel superalloys. These metals have been refined to their very limit, allowing engines to become more powerful and efficient. But the laws of physics tell us that heat is what unlocks more power, and nickel alloys are reaching their thermal ceiling, at around 1050 degrees Celsius. This forces us to search for a new class of materials. Therefore, we've found an incredibly promising candidate in niobium. With a melting point of 2468 degrees Celsius and a moderate density of 8.56 grams per cubic centimeter, niobium could allow engines to operate at significantly higher turbine inlet temperatures, improving thermal efficiency and the thrust-to-weight ratio. But niobium has a fundamental enemy that directly attacks its greatest strength: oxidation. At temperatures above 500 degrees Celsius, niobium exhibits catastrophic pulverization, a phenomenon known as pesting. The material disintegrates, forming voluminous oxides that destroy its structural integrity. This isn't superficial damage, it's an intrinsic chemical vulnerability. Unlike nickel, which creates a protective oxide layer, niobium forms oxides like niobium pentoxide that are not stable. Therefore, oxidation not only consumes the material, but it also creates cracks on the surface, drastically reducing the blade's fatigue life. This effect is a damage multiplier as oxygen diffuses along grain boundaries and creates stress concentrators. The obvious solution is to apply protective coatings. In fact, promising silicide-based systems have been developed. But the problem isn't that simple. The coatings must remain adhered to the niobium and withstand the extreme thermal cycles of an engine without cracking or peeling off. The disparity in the thermal expansion coefficient between the coating and the niobium can cause the coating to fail. And if oxidation weren't enough, niobium presents another fundamental challenge: its room temperature brittleness. This is due to the nature of the intermetallic compounds that make up niobium alloys. Their ordered crystal structure limits the slip systems, making the material brittle and prone to cleavage fracture. Therefore, this inherent brittleness directly affects its toughness and its impact resistance. This means that a critical safety event like a bird strike or foreign object debris, FOD, could cause a catastrophic failure, but engineers have found ways to mitigate this. The solution involves adding alloying elements or manipulating the microstructure to introduce ductile phases that can absorb energy. Therefore, a material can be created that acts as a microcomposite with a brittle matrix hardened by ductile niobium particles. But this material's engineering is a complex optimization problem where improving one property often compromises another, like high-temperature strength. This all leads us to the biggest obstacle of all: manufacturing. To create the most advanced turbine blades, combustor liners, or nozzles, the industry perfected investment casting. This method, where molten metal is poured into a ceramic mold, allowed us to control the microstructure of the final component. It was an astonishing breakthrough. From there, the evolution led us to directional solidification. With this process, engineers carefully manipulate the temperature gradient to force the crystalline grains to grow in a single direction. The result is blades with columnar grains that are extremely resistant to creep, since the grain boundaries, the weak points, are not aligned crosswise to fail under centrifugal force and high temperature. The pinnacle of this technology is single crystal casting, where the entire component is a single, perfect crystal. With no grain boundaries at all, these blades are the strongest and most creep-resistant that can be produced. Therefore, these methods are the foundation of current turbine engineering. But applying these techniques to niobium alloys is a technical challenge of astronomical proportions. Niobium refuses to behave like nickel. Its melting point of 2468 degrees Celsius, almost double that of nickel, demands a casting environment that is, in itself, a technological feat. Molten niobium is so reactive that it would attack any conventional ceramic crucible. Therefore, to prevent oxygen contamination, casting must be done in a near-perfect vacuum, far beyond what is needed for nickel. Any trace of oxygen or nitrogen dissolves into the niobium, forming inclusions that make it extremely brittle, ruining the part. The same problem presents itself, in an even more complex way, in laser additive manufacturing. Although 3D printing offers us unprecedented design freedom, the rapid fusion and solidification of the niobium alloy is a minefield. The process can generate internal porosity and undesirable microstructures that compromise the part's integrity. Segregation of alloying elements becomes unpredictable and rapid cooling induces massive residual stresses, exacerbating the material's inherent brittleness. Therefore, the old method of trial and error in the lab is too costly, slow, and prone to errors to solve the niobium challenges. We could spend decades making thousands of expensive alloys, melting them, and testing their strength to see if they work. But this is where modern engineering gives us a solution. The answer isn't a new furnace or a crucible, it's a total paradigm shift. Integrated Computational Materials Engineering, or ICME. ICME is not just a software tool, it's an approach that integrates databases, materials modeling, and multi-scale simulation. The idea is simple in concept but revolutionary in practice. Design a material and its manufacturing process simultaneously on a computer before producing a single part. ICME allows us to simulate the atomic behavior of niobium, predict how alloying elements will react, and how crystalline phases will form under extreme conditions. With ICME, we can model the fusion process in additive manufacturing and predict, millisecond by millisecond, the formation of pores and residual stresses. Therefore, we can optimize laser parameters virtually, drastically reducing the number of physical prototypes. In the case of oxidation, ICME can simulate the formation of oxides and predict which alloy composition or coating will generate a more stable protective layer, eliminating the risk of pulverization. Cutting-edge companies like Questech Innovations are leading this field using ICME in partnership with niobium suppliers like CBMM to accelerate the search. Therefore, ICME is shortening the material development curve from decades to just a few years. But ICME is not a magic bullet. The models are complex, require massive computational power, and must be validated with rigorous physical tests. It's a long-term strategic investment, not an instant fix. Still, ICME is the only viable path we have to transform niobium from a promising lab metal into the foundation of the next generation of jet engines. Niobium's journey to become the supermetal of the future is a reminder that science and engineering are a process of overcoming obstacles.